with the Global Modeling and Assimilation Office at NASA. Her research focuses on understanding the role of the cryosphere in the Earth system, including how glacial meltwater can alter the dynamic response of ice sheets. And we were just saying that there is a lot of potential connection possible with iHeart researchers. So very excited to welcome Dr. Andrews.
Great, thank you, Vandana. Let me just share my screen really quick. There we go. You should be seeing my screen right now, and apologies if I look off to the side. I have a second monitor, so I am paying attention, and obviously I'll be talking, but just to refer to a couple notes. So as Vandana said, I'm Lauren Andrews. I'm a research scientist in the Global Modeling and Assimilation Office at NASA Goddard, so I'm sitting down here a few miles south of you guys. And today I'm going to be talking about generally some of the work that we do in GMAO, and then specifically about the PolarMERRA reanalysis project, which I think, which I lead, and which I think has a lot of connections to the research that you all do to improve our understanding of the polar regions. So the figures and text and information I'm going to be showing you is the result of work from many people and many collaborations. So I will take all of the blame and none of the credit for anything that I say. But my goal here is to make for a nice conversation. If you have any comments or anything is unclear during my talk, please feel free to unmute yourself and just interrupt me. I'm pretty good at starting back up. So with that, I am gonna go ahead and just jump into my talk. So I always like to start my talks talking about what GMAO does. So the Global Modeling and Assimilation Office here at Goddard is an entity, and a large number of people, about 100 people work on this model, but our goal is to use a family of numerical Earth system models and many data assimilation techniques to enhance the use of NASA data across the globe. And so the Goddard Earth Observing System, or what I will refer to as GEOS, is an Earth system model. And I always like to say that an Earth system model fits in between process-based models, say of ice flow, perhaps of soil moisture and water propagation through the soil system, or chemistry, and a climate model. A climate model really is designed to project large-scale characteristics of the Earth system well into the future, while process models are really focused on understanding the small details of how, say, ice flows or how land surface evolves. But the Earth system model sort of sits in the middle between these two, and it is a combination of often different models. In GEOS, we have the GEOS atmospheric model, but we couple to a variety of models I'll talk about a little bit further. And its goal is to really represent processes that are relevant to the variability of the Earth system, including anthropogenic effects and effects of different global components, whether that's sea ice, the ocean, land, atmosphere. The models or the modules that represent these processes can be very complex, or they can be very simple, depending on the goals of a particular Earth system model. So our GEOS system is not just an Earth system model, it's an Earth system model and a series of data assimilation techniques. And I'm sure you are all familiar with data assimilation, but I actually only learned this when I started in GMAO. And so I always like to describe it because it helps me better understand it. And hopefully for those of you who don't know what it is, gives you a better sense of what it is. So data assimilation is an approach that is used to combine essentially observations, whether that's from satellites, from in-situ observations like weather stations on the ground, or ship-based observations, or airborne observations, into an Earth system model such that we get the best result we possibly can for a given variable in a given location at a given time. And in the simplest form, how an assimilation is run is that you run a forecast. So you run a free running model time step. Then at any particular location for any particular variable, you look at the difference between what the model produces and what the observations say, and you take that, what we call an increment, and you take that increment, you go back, you apply it into the model, and then let the model run forward. So it has a better initial state. There are many ways to do this, all the way from very simple, where you just directly insert those observations, to much more complex techniques that take into account the uncertainty in observations, the number of observations, their potential spatial impact, and many other characteristics, such that you have a more wholesale representation of what those observations mean. And we use a variety of techniques, whether from the land, through the atmosphere, and into the ocean, to assimilate data within our system. Yes, we have this GEOS-Earth system, or the GEOS model, the GEOS-Earth and data assimilation system. We do a variety of things with it, right? We assimilate variables across the land, across the ocean, across the atmosphere. We're starting to assimilate observations from the cryosphere as well. All of our development is open, and we release all of our model tags publicly. You can find us on GitHub. You can download, build, compile, and build our model, but it's best run on a supercomputer. Within our system, we have a series of modular components. The idea is that you can slot in different types of models as needed for different purposes. Overall, we have the GEOS atmospheric model as our primary model, and that's coupled to MOM6 or MIT GCM ocean models, or a data ocean if we're only focusing on the atmosphere. We have a land process model. We also can couple to SICE6 for sea ice evolution. We also have chemistry modules, and we're working on integrating ISSM within our system as we speak. So that's all well and good, but what do we actually produce, and what might be useful for you? So our main goal is reanalysis development and production. So, right, a reanalysis is that combination of the model and the observations through a data assimilation. We really need to, our mission is to leverage NASA data and other Earth system data to the fullest extent possible to get the best possible answer for any particular variable over any particular time. As you might know, MERRA 2 is our flagship reanalysis currently. We have been producing MERRA 2 since 2016, and it will continue on until it's superseded by MERRA 3, which will be a fully coupled system instead of an atmospheric only reanalysis. But we also do things like weather prediction and subseasonal to seasonal prediction. And here's a nice example of that. This is a forecast from yesterday for today's weather conditions across the United States. And you can actually find all of our weather forecasts here at this link below. The main goal of our forecasting systems is not operational, like say the National Weather Service, but actually scientifically oriented. So looking at how different observations and different parameterizations improve or degrade our ability to forecast certain conditions, whether that be weather or subseasonal to seasonal forecasting. We do observing system science. A great way to think about this is if you want to build a satellite and put it up in the air, it's probably a good idea to know how much of an impact it will have on our ability to model the Earth system in a reanalysis or in a forecast. So we have a way to essentially create a future satellite and integrate those observations into our system. And that provides insight into how observations may or may not be helpful in certain circumstances. We provide satellite mission support, both through providing atmospheric conditions and corrections to particular satellite products, and also through the production of certain products, level 4 products, like the SMAP level 4 soil moisture product is a combination of the GEOS data assimilation system and SMAP retrievals. We also do a host of basic and applied scientific research and development. So if you have an interest in the cryosphere or an interest in essentially any aspect of the Earth system, you'll find a niche here at GMAO. So now I'm going to start diving into what systems we have and then specifically focus on PolarMERRA. So along the top here are our different versions of our geosystem. And these numbers don't mean anything to you. They just are when we have particular upgrades that improve parameterizations, improve or introduce new data sets that we assimilate. And then here in these large boxes are our reanalysis products. And as you see, we have MERRA 2, which has nicely retired. MERRA, which is nicely retired. We have MERRA 2, which is currently in production. GeosR21C, which is going to be our new reanalysis. I'll talk about that in a moment. And then MERRA 3, which is our future fully coupled reanalysis. So we have dynamical representation of nearly every land, ocean, and atmospheric process that we can. And we expect production to start for this in about 2026. And below this, we have small boxes, which are related to what we call replays of our reanalyses. So we have, so a replay is simply using the information from the reanalysis instead of the observations to force a different model. So it's similar to a reanalysis, but requires less computational expense, which is nice and allows us to run things a little bit quicker at higher resolutions than we normally would be. So we have a reanalysis focused on atmospheric chemistry. And then we have the MERRA 2 ocean reanalysis, which is MERRA 2 observations forcing a dynamical ocean model, the MOM6 model, and a sea ice model. And then for GeosR21C, we have a chemistry downscale or a chemistry model, and then we have PolarMERRA downscaling, and I'll be specifically talking about that in a little bit. And this downscaling is really a way to introduce new improvements to our polar parameterizations and provide a high resolution product that is targeted to the cryospheric community. So as I mentioned, PolarMERRA will be a replay of GeosR21C. GeosR21C sort of bridges the gap nicely between MERRA 2 and MERRA 3. It's an atmospheric only reanalysis, so it has a representation of the land, or sorry, it has a model of the land surface, but it has just a parameterization for ocean sea surface temperatures and sea ice representation. So it's a little bit simpler than a fully coupled system that like what MERRA 3 will be. But it can still provide a lot of insight into what's going on in near surface conditions across the globe. The main goal of GeosR21C is to leverage a lot of new observational platforms that NASA has launched in a very short period of time. So we're going to have this replay that goes from about 1998, and it will go through present until we start MERRA 3. And we really see this as an opportunity to test new ways of doing things and provide a higher resolution data set than MERRA 2 with more and more observations. It's always our goal. So PolarMERRA in itself is a research project that is designed, that brings together researchers in the Global Modeling and Assimilation Office and the Cryospheric Sciences Lab to improve the representation of polar processes. We're in a series where we have a series of steps of development that we're working through as we speak. The first stage is the development of an assessment framework and really working to improve polar parameterizations within our system. The second is the replay that I talked about, and that should start running sometime in early 2024. We're looking forward to that. And then finally, it's a transfer of knowledge and information, both through the development process and through our, a series of high resolution validations, but also getting feedback from the community, including you all. So why PolarMERRA and why now? Well, we acknowledge that MERRA 2 reanalysis outputs are really insufficient for the cryospheric community. The variables for process studies are lacking. I think a really great example of that is we don't actually, in MERRA 2, we don't output meltwater, which is a critical component. We output runoff, but not meltwater. And that's impacts how people can use ice sheet information. Our resolution is insufficient. Right now, MERRA 2 is output at about half degree, so about 50 kilometers. And then there are a whole bunch of what I'm going to, for lack of a better term, consider heritage parameterizations across the cryosphere, whereby they're simple representations that have values or have been tuned to the mid-latitudes, and so don't do as great a job of representing what's actually going on in the cryosphere. The other reason is that we know that we have large biases in temperature and precipitation across the Arctic. And improving that is an important part of what we're doing as part of PolarMERRA. But I think we should always be considerate of what we don't have, and that is really, polar observations are sparse or they're short, and that can make it very difficult to validate the data that we produce as part of a reanalysis. And it also makes it just more challenging within an Earth system model to justify cryospheric changes, because you want to minimize any negative impact on the mid-latitudes when you make these changes. So you might make changes that are perhaps less grounded in all of the observations than you may otherwise if you were only focused on the polar regions. So I'm going to talk about 4 quick examples of what we're doing in PolarMERRA. These are going to be incomplete examples because we are still running tests and we're still exploring sort of the impact of many of these changes on our system. But first, I'm going to talk about polar precipitation, what it means for near surface conditions, particularly over sea ice. Then I'm going to talk about how we're improving the representation of sea ice within the geosystem. I'll talk about an interesting problem we found in the land ice related to some large-scale updates that happened globally. And then finally, I'll talk about the resolution that we expect PolarMERRA to be, when we will start producing it, and so on. So we know that MERRA 2 tends to overprecipitates globally. We actually apply a correction to the model precipitation that is fed to the land in order to better represent this precipitation. Because in the Arctic and the Antarctic, we have limited amount of data to correct the precipitation, we don't correct that precipitation. So we have a tapering of our precipitation correction that starts at about the southern tip of Greenland. And that excess in precipitation has been documented throughout the literature. This is a really nice example of it by Andy Barrett, where he's taken in-situ observations across Arctic sea ice and looked at the bias for different reanalyses. And I'll just highlight that MERRA 2 here is in red. And you can see that consistently over a long period of time, about 10 years, for each month, MERRA 2 sticks above, or in one or two cases, just at the 100% bias. So we see this bias, it's more persistent in the summer, but it's there. This bias is caused by an excess of drizzle in our model. And that means that there are many, many days where there's just a low level of precipitation falling across the Arctic. This impacts near surface humidity, near surface temperature, accumulation rates, the list goes on. So we know this is a problem, and you can see here, this is drizzle precipitation for all of these reanalyses, and MERRA 2 sits right up here, just too high. So one of the first things that happened in the development for R21C and PolarMERRA is we provided an update to the cloud convection parameterization and cloud microphysics to reduce both low and high intensity precipitation rates. And that's really paid dividends in the polar regions. So globally, what we see here is our observational data set in black, our GPM iMerge data set. And then here is our candidate and our control run. So a candidate system is the system that will be used for R21C and PolarMERRA. And what we see is that we do see a slight decrease in the frequency of low precipitating events and a decrease in the high precipitating events. And we can see the impact of those results when we look at the spatial pattern and the temporal pattern of precipitation. So here, this map on the left shows our candidate PolarMERRA system minus MERRA 2. And we see a reduction in precipitation over the Arctic, over Greenland, and over some land areas. That's really great. That's what we want to be seeing. This tuning parameterization, these tuning improved parameterizations made, what might look like a small impact, but millimeters per day is pretty substantial when you start to think about it. And indeed, again, MERRA 2 here in red, but our candidate system falls now nicely within the spread of the reanalyses that are available. And so we are seeing an improvement in precipitation. So that's great, but I'm actually, in a little bit, I will give you a little demonstration of how that can be a confounding problem in our system. So precipitation, we've made some improvements. There are some good impacts, and I'll show you a bad impact. The other thing that we are well aware of is that we have a warm bias across the Arctic in MERRA 2. And that's illustrated nicely by this plot from Lynette Bossevar, which is the MERRA and then MERRA 2. So the red bars are the one you want to pay attention to. 2-meter air temperature difference. And you can see, particularly in the winter months across the Arctic Ocean, we have a several degree bias overall in our temperatures. This example is for 2012, but this persists through multiple years. And indeed, even in our candidate system, that while we have a reduction, we do implement new radiated transfer models for both shortwave and long wave, and it's really impacted our long wave radiation and reduced our wintertime temperatures across Arctic sea ice, which is ideal. The problem is we still have air temperature biases that we need to resolve. That can be seen in this plot here on the left, which is the sea ice skin temperature bias of our candidate system minus MODIS, so our MODIS skin temperature for March. And what we see is that our skin temperature biases can be upwards of 4, 6, 8 degrees Kelvin. And that's because we have a really simple parameterization of or representation of sea ice. And within the GEOS system, within the atmosphere only system, we simply represent sea ice as a 7-centimeter slab that integrates incoming and outgoing shortwave and longwave radiation, and the energy balance of budget of the sea ice and its temperature is actually relaxed to 0 degrees over 24 hours. So it's forced towards 0 degrees over a 24-hour time period. The idea being, and this is one of those heritage parameterizations, that the ocean temperature is close to 0, which is not true. It's close to negative 1.8. But that relaxation then allows for both a seasonal cycle or a diurnal cycle, but also provides a heat flux from our parameterized ocean to a parameterized sea ice into the atmosphere. So we provided a series of tuning experiments. We tested a series of tuning experiments where we looked at changing the ocean heat flux and modifying the temperature by which we relax to. And we can reduce the overall bias in the Arctic in terms of skin temperature, and that's seen here. The problem is that it's not, it is, the sea ice thickness plays a role. So we see overall, we're really reducing the temperatures reducing the temperatures too far in certain regions, but not far enough in other regions. And it seems to be correlated with sea ice thickness. So we're actually working now to introduce a parameterization of or a climatology of sea ice thickness along with our sea ice concentration parameterization so that we have a better representation. And tests are ongoing as we speak. So I'm going to switch tacks a little bit, and I just want to make sure, because my WebEx has sort of like frozen a little bit, but I want to make sure you can all hear me. Nikki, could you just let me know if that's the case?
Perfect, we can hear you.
Great. Okay, that's good. So now we're going to look at surface air temperatures and melt across ice sheets. And one thing that I do want to bring up is that MERRA 2 actually performs pretty well in terms of surface temperature and melt across land ice surfaces, given the resolution that it is produced at the half-degree resolution. So in many instances, our results are actually comparable to some regional climate models and reanalyses. And this is a nice example of that here on the right from a paper by Richard Colither, looking at a particular melt event where we see the observations in solid and our MERRA 2 results in dotted lines. You can see really well, in most cases, we do capture the diurnal variability and capture the magnitude of 2-meter air temperatures. And we do a reasonable job of capturing the melt pattern relative to MODIS observations here. But we know that the reason why we do a good job of estimating near surface temperatures across the ice sheet is because we have a series of compensating biases within our system. And so here is the net long wave, short wave, latent and turbulent fluxes compared to a single weather station, KNU, which is in southeastern or southwestern Greenland, but up in the accumulation zone. And you can see here's the net difference. We do reasonably well, but we do have these biases where we have a reduction in long wave, or a lower long wave, higher short wave, and higher turbulent fluxes, and we would really prefer. And this comes back to play in that cloud and long wave parameterization that I talked about at the beginning of the talk, because they have complicating impacts. We reduce the amount of long wave radiation in our system, or sorry, increase the amount of long wave radiation. So we're actually seeing an increase in air temperature in our candidate system across the ice sheets, or anywhere we have snow cover or glacier cover. And you can see that here in this plot, which is 2-meter air temperature of MERRA 2 minus our PolarMERRA candidate system. And we wanted to figure out why, because the pattern does not match up with the changes to our long wave radiation parameterization. So I am going to just step through sort of a quick thought process where we compare our candidate system and MERRA 2 to series EBAF, which is an energy balanced cloud filled satellite product that is used to validate top of atmosphere model outputs pretty consistently. So we know series EBAF does have some artifacts and potential biases over the ice sheet, but we're just going to use this in a general sense to illustrate the problem that we have within our system. So this is our total top of atmosphere albedo here for MERRA 2. So this is our analysis, so MERRA 2 minus series EBAF, and then this is our candidate system minus series EBAF. And so what we see is that overall we have a decrease in our top of atmosphere albedo. And this is particularly true here along the northeastern coast. That's actually because we changed some glacier tiles to land tiles. So that red is expected, but these other, this increase in green is not expected. So why is that? If we look at our total top of atmosphere minus our clear sky top of atmosphere albedo, so the impact of the cloud radiative forcing, what we see is we do see an increase in that cloud radiative forcing due to our changing cloud parameterizations and our implementation of new radiative transfer models. So this is overall sort of what we expected. But what we actually see is when we look at the clear sky top of atmosphere albedo, which is similar to the surface albedo on the ice sheet, what we see is that we really do see a darkening across the ice sheet. And this was unexpected, and it took us a little while to sort of piece together. And in fact, it's darkening an already too dark surface. So reanalyses and MERRA2 in particular are known to have a dark albedo bias. And that's because of the way we parameterize albedo related to snow density. So we have an overdark surface. We've increased our downwelling long wave in our new candidate system such that the biases in our shortwave and sensible heat fluxes are overcompensating, and we're warming that surface. And this is actually due to the cloud parameterization tuning that reduced the amount of precipitation across the model. So we actually are seeing fewer snowfall events, which means we have less bright snow, particularly across the summer months, which is really darkening our surface and increasing our near surface temperatures. So we are going back and retuning our polar snow densification schemes and looking very carefully at how we parameterize fresh snow density across the ice sheet to better represent observed albedos and really reduce those shortwave biases that we see across the ice sheet. So those are sort of two, examples of how we're dealing with particular problems within the reanalysis system that we are developing. And part of the, all of these, problems have been persistent for a while and hopefully will be remedied into the future. So if you have any insights or thoughts or approaches, we'd love to hear from you. Please reach out. So as part of PolarMERRA, we are really focused on providing a higher resolution product. I think that everyone who's worked in the ablation zone or along the sea ice edges understand that if you have a coarse resolution reanalysis product, it doesn't provide the variability in space or in time of certain model or certain output characteristics that are actually necessary to interpret data in a reasonable way. This is, I work mostly with ice sheet runoff. So this is a particular problem along across the ablation zone that actually, is maybe in MERRA2 1 or 2 pixels wide, which isn't very useful in terms of data. We can downscale that using different techniques, including machine learning, but we prefer in GMAO to run a downscaled replay, which is what we're going to do for PolarMERRA. And by running a replay, it allows us to downscale while maintaining internal consistency across our parameterizations. So we're not adding snow, we're not removing snow, for example. We're not, increasing runoff in total for the system. We're just better distributing it across, a higher resolution. So PolarMERRA, we're targeting sort of a 6-kilometer horizontal resolution. It will have 72 vertical levels. And really this value, the 6 kilometers, is determined by the complexity of our physics parameterizations. Any higher resolution, and there are some parameterizations that really should be changed to be better representative of, smaller scale processes and also balancing computational needs. It's going to be run from 1998 to about 2025, whenever we switch to MERRA 3. And one of the things we've done is really improved our polar collections. So you have all of the information to balance the mass and energy budget of any cryospheric process that we represent within GEOS now. So we're starting soon. And with that, I just have one last slide, right? PolarMERRA is a series of steps. The goal is to improve polar processes in a well-documented way and in a way that feeds well into our future reanalyses. I think that anyone like myself who has been a cryospheric scientist and then moves into the realm of Earth system modeling kind of realizes that like the polar regions get forgotten occasionally. And our goal here as part of this project is to ensure that doesn't happen into the future. And then to sort of spur conversation, and I've left enough time to have conversation with those of you still here, is, you know, where I personally and also GMAO is looking toward data science and machine learning to better understand processes across our Earth system model, and in particular for the cryosphere. I really love the idea of, you know, improving on PolarMERRA. So if you guys want to, you know, provide high resolution downscaling, I think that's a great idea. We have high resolution satellite products that can be used with techniques to provide better outputs of particular variables. We use it internally to assess for model deficiencies in advance of data assimilation. So one of the things that we are doing right now is using SMAP melt retrievals to actually then develop a machine learning model using our atmospheric forcing to better understand where we are getting melt versus where we're not getting melt in our model and what is causing that. I think that you know, data science also has the ability to inform us about unresolved model characteristics, whether that's resolution, issues resolving around how we smooth or don't smooth topography within our model at a certain scale, whether we represent certain processes across glaciers and ice sheets or sea ice, such as debris cover. And then one of my favorite ways, and we're doing this within, we do produce a chemistry forecast. So for like PM 2.5, is integrating local knowledge and vulnerability to provide better, more targeted predictions and information to local communities. So we take our chemistry model, forecast model, which is run at a relatively coarse resolution, and then use a variety of techniques to leverage multiple in situ observations in particular cities to downscale and increase the temporal resolution of our outputs so that they're actually relevant for community decision makers. And I really see perhaps thinking about how to do this in terms of vulnerability in the Arctic could make a really large impact, whether that's, you know, using information from reanalyses or forecasts that include wind to provide a better, higher resolution and local information about storm surge and wave erosion to provide better information about, you know, expected sort of impacts of particular storms to local communities and so on and so forth. I think there's a lot of opportunity there. So with that, I will stop talking and hear from you. So thank you very much for all of your attention.
Thank you so much, Lauren. This was very, very informative. My mind was churning as you were talking, and I was messaging my students to be here and listen to your talk. So I have a lot of questions, but I want to see if anybody else wants to start with questions. I think Sahara has a question. Sahara, do you want to speak out?
Let me see if I can find the chat too. I think I saw it. I think it was, how do we run replays? So I am not an expert at running the replays. I know how to do it, but I can inform you about sort of our process. So in traditional reanalysis, right, you're using those direct observations. And in a replay, what we do is instead of using those observations and having to go through the process of, you know, error analysis and estimation as part of the reanalysis, we run a replay. And what we do is we use we smooth the large scale atmospheric forcings from a previous model, say MERRA 2, or in the case of PolarMERRA, R21C. And there'll be values like sort of 500 millibar heights, 500 millibar wind speed and direction, high level temperatures. So sort of atmospheric characteristics that can provide insights about sort of storm development, directionality, overall weather conditions. So we then what we do is we use that as the increment to our system, apply that increment to our new model system. So when I was describing how when we do data assimilation, you run the model forward, you look at the difference between the observation and the model, and then take that increment and then go back and apply it. We do that, but we use that increment from a previous model. It reduces computational need, and it in particular provides sort of just smooth and maintains sort of large scale characteristics, but allows really local development to occur.
There was a second part to Sahara's question as well,
okay.
On the benefits of using PolarMERRA sea ice data over NSIDC data.
Okay, so I think the first, that's a really great question, and this is something that we always try whenever you talk to someone in GMAO, which is like myself or Richard co-author. It depends on what your goal is, right? You don't want, we in MERRA 2 and in our atmospheric reanalyses, we actually prescribe sea ice concentration from NSIDC, and then we grid it to a particular resolution that we use within our model. So if you are looking at our atmospheric reanalyses, so MERRA 2, R21C, you are better off using NSIDC sea ice. If you are interested in sort of the relationship between the atmosphere and ocean forcing and sea ice characteristics, I would suggest we're going to start making publicly available our MERRA 2 Ocean, which is a weekly coupled ocean reanalysis system where we actually have a dynamical sea ice model. So whenever you're looking for sea ice and characteristics in particular, be very careful looking at any reanalysis, whether that's ERA 5, ERA interim, MERRA 2. If they're atmospheric reanalyses, they're going to prescribe sea ice characteristics. So in that case, use NSIDC, and that's going to be your best bet.
Okay, great. I see lots of questions on there too, but I saw hands up from Sudeep, Anish, and Jianwu, so maybe we'll have some participants speak up. So maybe Sudeep, you want to start?
I cannot hear you. If you are.
Hear me now?
Yes, yes.
Okay. So I have a question. You talked about PM 2.5. So
my area of non-expertise.
Oh yeah, like I know Arlindo was talking about that they are working on PM 2.0, aerosol deposition on ice. So do your data, do you think it will have something like aerosol deposition on or concentration on ice surface or something?
Yeah, so that is something that we are working toward, is using a prognostic aerosol deposition. Arlindo is probably very positive. That's really in the development stages. We have the framework. We just, how you represent your initial albedo and how you deposit things really matters. And it matters a lot in terms of atmospheric temperatures. We can send our system into snowball Earth if we don't get it correctly. So it's requiring a lot of development and a lot of tuning. So we don't expect it to be in PolarMERRA, but as we are improving how we represent ephemeral snow and Arctic snow through some data assimilation of snow cover fraction and improving our snow depletion curve so that we better capture SWE, that matters too. We hope to then integrate it into sort of MERRA 3-ish sort of territory. So it is on the docket. It's just not, it's something we're working toward.
Yeah, so. Right, I got it. Like, because I was working with him on aerosol atmospheric river, which is aero data. And now he wants to say, he said like, let's look at up like how is going. Are you studying aerosol deposition because of the rivers? I'm working on that, and if I have some results, I'll talk to you sometime. Maybe we can chat on that.
Yeah, I think that, right, we do have chemical transport in the atmosphere. It's that deposition component and modeling that deposition with melting and accumulation that we're working on. So
Okay, thanks.
Yeah.
So maybe Anish. Anish, do you want to ask your question?
Hi. Yeah. Can you hear me okay?
Yes,
Great.
I
Yeah,
can.
thank you. Great talk, Lauren, and lots of information, like Vandana said. I was wondering more about logistically the timeline for this. You mentioned it's dependent on the R21C, because here with a student here, a computer science student at CU Boulder, we're looking to downscale ERA 5, and there is a CARA reanalysis.
Yes. Yeah.
CARRA for over Greenland, right, which is at 2.5 kilometer. But it's harder to work with because it's a regional reanalysis without a global span, and it's on a different projection. It's harder to work with machine learning for. I was wondering about the timeline for PolarMERRA, if you have any more information,
Yeah.
and how to access the data once it's available.
Great. Yeah. So first off, the CARA reanalysis is great. And I will also, if you don't know, they're going to start CARA 2 in probably a year and a half from now, which will be more Arctic coverage than the sort of 3 regions they have right now. So, keep that in mind.
Okay. Yeah.
There are some differences between PolarMERRA and the CARA reanalysis that has to do with some data types that are assimilated versus not assimilated and things like that. PolarMERRA, we're planning on starting production in early 2024. Honestly, we are really, there's a lot of waiting right now for computational resources because they're changing over some cores. So things might shift a little bit, but we're doing the best we can to get it out as soon as we can. And it will be global, which is nice, covers Greenland and Antarctica. So yeah, that's the timeline. If you're interested in sort of data that we have produced as part of our validation, which may be at a slightly coarser resolution, or for sort of shorter windows of time, reach out and we can see what we can do.
Okay, will do. Thanks a lot.
Yeah.
Jianwu?
Yeah, a great talk. I have 2 questions. One is similar to what Sahara asked. We data science. We trying to understand the relationship between the data variable, maybe prediction or forecasting. So we have 2 types of data we can select. One is observation data, like MODIS. You were showing it. One is reanalysis data, like MERRA to ERA file. I wonder you mentioned a little bit, but still I want to know if we want to do data analysis, maybe correlation, maybe forecasting, which data we should use for those kind of machine learning tasks. Can you explain the differences?
Sure. So I think for this purpose, we produce 3 potentially relevant products. So there's MERRA 2, which is a reanalysis, which is all in the past. Essentially, we have a 10-day latency on our production. And then we have our short-term weather forecasts, which are run 4 times a day, and they're only produced for, they have a 5-day forecast period. If you're really looking at understanding like projections, our sort of, we're an Earth system model, so we don't do long-term projections, but we do subseasonal to seasonal projections. So that's out to 9 months. And we have a system that is actively running in production right now. It's our version 2 system. And it is based off the forecasts are produced off of a weekly coupled atmosphere ocean reanalysis. We take those initial conditions and we set off our forecasts. They have an ensemble. Right now we use an ensemble of 10 members. We're upgrading to our new version within the year, which is version 3, which will have an ensemble of 40 members. So we have a lot of data. Those are forecasts. Can you, sorry, elaborate? Did I answer your question?
Yeah,
And then two, what's
you mentioned the different projections of how,
yeah.
but how what's in comparison with observation data like MODIS, which in your idea, in your opinion, in which cases we should use MODIS data like observation data, and which cases we should use real analysis data like MERRA2?
Yeah, so in which cases to use like MERRA2 versus like MODIS? Is that what you're
Yeah.
asking?
Uh-huh,
Yeah, so I think one way to think of it is that they're complementary. Right, MODIS has, MODIS needs an algorithm to process for melt in particular versus we produce runoff in MERRA2. We will produce melt and runoff in our future systems. That is based on the energy balance at the skin surface of the ice sheet. So I think like a way to think about this in a complementary way is there was a recent paper by the RACMO the RACMO group, which is a regional climate analysis focused in the polar regions over Antarctica, where they use the atmospheric conditions of a particular model, RACMO, and then use information about albedo and melt from satellite observations to downscale RACMO to that very high resolution of MODIS. So that 500 meters. And then see, you can use that and then look back and see where are we doing better, right? Because MODIS is primarily an albedo product, which is shortwave, which is only part of the energy balance. It provides insight also into where that, where shortwave matters versus, or when or where shortwave matters versus long wave. So I think you can think of it in a complementary sense. The nice thing about reanalysis products, whether that's MERRA2 or ERA5, whatever, is that you get complete temporal and spatial coverage at every single time step, which is absolutely, as incredible as MODIS data is, they can't produce that. So we're just at a coarser resolution.
Cool. Second question is just this slide you were showing how data set helps this in real analysis data. I know there are efforts doing bias correction. They have some climate model, and they are comparing with the observation. They are even deploying machine learning model to predict the difference. They don't trying to use machine learning to replace the climate model. They predict the differences. Do you think that is a way, for example, if I use the climate model and I read like observation and trying to predict the differences, I don't have idea yet, but similar like the bias correction approach could be used for this real model improvement?
Yeah, so I think that, first off, I will say that like bias correction and downscaling are absolutely a critical component of, linking Earth system models to, process-based studies. I think a really good example of that, there's a recent paper by David Rounce that looks at projections of glacier mass loss into the 21st century at different, with different forcing scenarios. But that data set, you need to have hindcasts so you understand what's going on. But you actually need to downscale and bias correct that data for individual glaciers, because no matter what, the frank reality is the computational resources that it requires to produce even a 1 kilometer resolution run of our system is pretty enormous. So that's where like really there is a machine learning. There's a gap that needs to be filled by a variety of techniques to bias correct. We know we have biases even in our reanalyses. So that matters, and correcting those biases to be more accurate for particular regions, particular times is really important. So using that information, leveraging one might be like snow accumulation across a glacier, right? Our snowfall, even at 6 kilometers isn't going to, capture the gradients and accumulation that matter for a particular glacier, because those, that SWE distribution is going to be dependent on a host of parameters, from the wind direction, shadowing, debris cover that we just don't represent, and that you can represent by taking atmospheric forcings from reasonably high resolution reanalysis data sets and forcing others.
Okay, thank you.
Great. I'm going to try and parse out a couple of questions from the chat. Humaira asked a question, I hope I'm interpreting it correctly, on any machine learning models that you have used. How did you select them, or any tuning parameters that you came across?
I am not a machine learning expert. You guys are the machine learning experts. So I'm interested to see what you think about that. I will not hazard to use machine learning language in a series of experts by machine, or in a room of machine learning experts. So I will stop there. We have inputs. I think that there are aspects of machine learning that can really better that can be used to better understand processes, period.
Great, thank you. And I think you alluded to this a little bit, but Naomi's question is around bias correction. And she's trying to understand, could you speak a little bit more to it, like why bias is an issue and why bias correction is important? I hope I'm interpreting the question appropriately.
So, I mean, we have biases, right? You see that in our precipitation record across the Arctic, and you see we also have biases in our surface temperature, right? So say, for example, the melt we produce over Greenland might be more extensive in our new system if we don't fix our surface energy balance problems. And in that case, right, using a bias correction, either via machine learning or using weather station to bias correct data, provides better outputs that can be used to interpret in situ data, to interpret sort of small scale process models. I'd like to, model, how meltwater goes through the ice sheet, right? So I have to have a good estimate of what that meltwater is before I put it into a moulin or a crevasse. If I don't have a good estimate, if I know it's biased, then my output of my model is biased. So thinking about bias correction in that way, making products more usable for you as a researcher or the community, I think that's a really interesting, it's an important component of, scientific development. We know we have biases. We can't correct them all. We try.
Other questions?
Maybe I can ask one more if nobody got any question.
Go ahead.
So, some people using some map to get this melt water, right? Or
yeah, I do. Yeah,
you do.
I do know about it. I'm not going to speak to being an expert at
okay. I was thinking if you know. Oh, that was I was thinking, like, if you know, like, map is for soil moisture. I was like thinking how accurate would that be over Greenland, because meltwater and soil moisture.
I mean, there are. I think Mike McFerrin was on here. He's probably better versed in sort of SMAP soil moisture retrieval, or not soil moisture, melt retrievals. I will say there is a heritage, like AMSR2 has been used to detect melt extent across the ice sheet. So those brightness temperatures can be used to detect liquid water. The details of that, I think Andreas Kollender just had a paper out recently that looked at that in particular and how that's done. So I won't speak to being an expert at all. If I sounded off like I was an expert, I apologize.
Yeah, I was actually referring to that data, but I was thinking if anybody has used that other than him, so yeah, no problem. Thanks.
I mean, I think you definitely use that data in certain ways.
You want to be giving a try if that works.
Great. So I have a follow-up based on all of the interest that your talk has generated, and there'll be lots of discussions, I'm sure, following up. Many of the student projects and many of the sub-projects in iHarp are using reanalysis data like ERA5.
Yeah.
And I'm sure you'll have a run of students emailing you possibly, but I want to kind of streamline it and see what could be some of the ways to partner. There are some elements that are already there where you may have the data, some elements that are coming up in 2024 timeline, as you mentioned. What could be a way by which we can connect with you more on either getting the data directly or getting involved more?
Yeah, so first I'll say, like, ERA 5 is also a great product. We make different choices, particularly in the Arctic, than ERA 5 does, or even over most land. We don't assimilate, surface temperatures. ERA 5 does, as an example. So, just be aware that ERA 5 has biases. We have biases. We are aware that they're very good at what they do. But if you are interested in our products, so I think the first thing to do is look at our webpage, the GMAO webpage. MERRA 2 is publicly available. Our weather forecasts are publicly available in NetCDF format. Our S2S products are sometimes available. If you are interested in using our subseasonal to seasonal forecasts, reach out to me. In terms of PolarMERRA, our products will be available, and we will also be providing a series of tools to analyze or look at the data. So that will be publicly available and via our website. Right now, if you're interested in sort of what we're doing and how we're doing it, feel free to email me. There is definitely not a problem with that. Say you're a student, and I will guarantee you will get an answer faster than anyone who's a professor.
Right, so maybe us professors will ask our students to reach out. I do think there will be a lot of interest because even using different reanalysis products, there could be different questions, or even like the comparative analysis you showed for the bias correction, we might want to do some similar studies as well. So it would be very interesting. I'm sure students will take you up on that. I'm just going to give out a last call for any questions. Any other questions?
No, so you have the S2S data, right?
Yeah, we do have S2S data. There's a lot of it.
A lot of it? Good.
There's a lot of it. So, we do retrospective forecasts all the way back to 1980. And they're 9 months long. And right now they're at a 1/2 degree atmosphere and 1/4 degree ocean. So if you're interested in those outputs, we do have a file specification on our website. If you look at that first and get a sense of what data you're interested in, that can help us a lot, because we have to pull it from tape if you're interested in using it. So it can take a while, but it is there, and we do we do our best to make it available for scientific use for sure.
Okay.
So
I'll have a look. If I have a question, I'll send you an email.
yeah, definitely.
Yep.
Wonderful. I think Anish said it best. Thank you so much for a great talk, and this is going to be a very useful resource for all of us. And this talk is recorded, so I'm sure we'll find more nuggets as we listen back to it. Thank you so much, Lauren.
Great. Thank you very much.
Wonderful.
Bye.
Everyone.
Bye.